According to the law 42 of the laws of cricket, the bowling of fast short-pitched balls is dangerous and unfair if they are likely to inflict physical injury on the striker, irrespective of the protective equipment he may be wearing. How could a small object like a ball inflict injury on a cricketer? The impact of a moving object differs based on its momentum, which is the product of the body's mass and velocity. A cricket bowling technique devised in the 1930s called body line involved aiming fast-paced balls at the shoulders of the batsman. In the past, many batsmen have been injured due to the impact of balls travelling with high momentum. In this lesson, you will learn about momentum and the second law of motion. At the end of this lesson, you will be able to identify the significance of momentum, state Newton's second law of motion, derive the expression for the measurement of force, and explain the impact of change in momentum in terms of impulse. To analyze the concept of momentum, let's compare the impact of moving objects in different situations. Observe the marble dropped onto the thin glass pane below. The glass pane is intact. But what happens if we drop a cricket ball onto this glass from the same height? Ouch! The glass pane shattered. Why did the glass pane shatter this time? What was different in the two situations? The height from which the marble and the ball were dropped was the same. So was the velocity of both the objects when they struck the pane. Clearly, it must be the bigger mass of the cricket ball that made a difference. As the mass of the cricket ball is more than that of the marble, its impact on the glass pane is higher than that of the marble, and thus it shattered the glass pane. Let's now look at another case where two identical marbles, say P and Q, are dropped onto a thin glass pane from different heights. First, we drop the marble P on a thin glass pane from a height of 1 meter. The marble P does not damage the glass pane. Now we drop another marble Q from a greater height. Wow! Dropped from a greater height, even this small marble has shattered the glass pane. Why was the glass pane shattered by the marble Q and not by the marble P, even though the mass of both the marbles is the same? As the height from which an object is dropped increases, the velocity with which it strikes the ground or any other reference level also increases. Being dropped from a greater height, the velocity at which the marble Q strikes the glass pane is greater than that of P. Hence, the impact of marble Q on the glass pane is greater than that of P. That's the reason marble Q shattered the glass pane while marble P did not have much impact on the glass pane. Based on these observations, we can say that the impact of any object on the other depends on two factors of the object causing the impact, namely, its mass and velocity. These two factors together constitute a physical quantity, called the momentum of a moving object. The momentum of an object is the product of its mass, m, and its velocity, v. It is denoted by the small letter p. Thus, you can express momentum as p is equal to mv. Momentum is a vector quantity. It is measured in kilogram meter per second or Newton second in the SI system and in gram centimeter per second or dyne second in the CGS system. Because of its momentum, a fast-paced cricket ball can hit and hurt the batsman, or the wicket-keeper, if the batsman is not able to play the ball properly. That's why batsmen on the cricket field wear protective helmets and body pads to prevent possible injury. Momentum helps us understand the impact of collisions and explosions. For example, it explains the impact of a collision between two trucks or a cannon firing. The greater the momentum of an object, the larger the impact is on the other object. Remember period films where we often saw columns of armies who used huge logs to break down the gates of a fort? The group of men holding the log goes back a fair distance from the gate. Then they run to the gate to ram the log into the gate for maximum impact. The velocity and the mass of the log together provide enough momentum to break the gates down. The momentum of this army column differs at different points in their run-up to the gate. Although the mass of the log is constant, their velocity is increasing constantly. That is, they are accelerating. Another example is when actors in movies perform stunts, such as breaking down a door. The momentum of an object increases when it accelerates. Therefore, the rate of change of momentum depends on the acceleration of the object. Newton's second law of motion states that the rate of change of momentum of an object is proportional to the applied force and takes place in the same direction of the applied force. Let's verify this law using an example. Observe this billiard table. The yellow ball is at rest right now. However, when the cue ball hits the yellow ball, it is set into motion. After being hit, the cue ball moves with less velocity, while the yellow ball moves with more velocity. Thus, there is a change in velocity of both the balls, that is, a change in their momentum. Additionally, the direction of motion of the yellow ball is the same as the direction of motion of the cue ball. Now let's observe what happens when the cue hits the yellow ball with more force. As you can see, the yellow ball now moves a longer distance than the last time, before coming to rest again. Thus, when the force applied by the cue ball increases, the momentum of the ball increases as well. Hence, we can say that the rate of change in momentum of an object is proportional to the force applied on it. A lot of our actions are based on the second law of motion. Observe the cricket fielder reaching out to catch a fast-moving ball. As you can see, he pulls his hands back to catch the ball. Why does he do that? He does that to reduce the impact of the fast-moving ball on his hands, before bringing its velocity down to zero. By pulling his hand back, he increases the duration of time taken in bringing the velocity of the ball to zero. Newton's second law of motion can be expressed mathematically as F is equal to ma, where F is the force applied on a body, measured in Newton in the SI system and in dyne in the CGS system. M is the mass of the body, and A is the acceleration produced in the body. Let's derive this relationship using an example. Consider a ball of mass m having an initial velocity u. When a force of magnitude F is applied on the ball for time t, the ball moves ahead with an acceleration a. In the time period t, the ball accelerates to a final velocity v. Let p1 be the initial momentum and p2 be the final momentum of the ball. By the definition of momentum, p1 is equal to mu. p2 is equal to mv. Hence, the change in momentum is P2 minus P1 is equal to mv minus mu, or m multiplied by v minus u. The rate of change of momentum is the ratio of change in momentum to time. That is, m multiplied by v minus u divided by t. According to Newton's second law of motion, the rate of change of momentum is proportional to the force applied. This gives us the relationship F is proportional to m v minus u divided by t. The acceleration a of the ball is the ratio of change of velocity v minus u to time t. Hence, we can write this relationship as F is proportional to ma. We use a constant of proportionality k to equate this relationship. Therefore, F is equal to kma. In the SI system, a unit force is a force with a magnitude of 1 Newton. Unit force is defined as the force that produces unit acceleration, that is, 1 meter per second square, when applied on a body of unit mass 1 kilogram. Thus, substituting the values in the expression, F is equal to kma, and simplifying, we get the value of k as 1. Hence, we get the mathematical expression of the second law of motion as F is equal to ma. Therefore, according to second law of motion, you can express the force applied as the product of mass and acceleration of the body. Using the expression for second law of motion, we can define the relationship between the SI unit of force, Newton, and the CGS unit, dyne. Consider unit values for force, mass, and acceleration of an object, and substitute these values in expression F is equal to ma. You get 1 Newton is equal to 1 kilogram meter per second square. Since 1 kilogram equals 1000 gram and 1 meter equals 100 centimeter, 1 Newton is equal to 10 raised to the power 5 gram centimeter per second square. Since 1 dyne is equal to 1 gram centimeter per second square, 1 Newton is equal to 10 raised to the power 5 dyne. Let's again look at the second law of motion. According to this law, force equals rate of change in momentum. Rearranging the expression, change in momentum equals product of force and time. When a large amount of force acts on an object in a very short duration of time, it is termed as impulse. Here is an example of a situation where we see impulse at work. Consider a cricket ball bowled towards a batsman in a cricket field. The batsman strikes the ball with a large force that acts on the ball for a moment. The impact of the bat enables the ball to change its velocity in magnitude as well as direction. This is the impulse of the bat on the ball. Impulse is numerically equal to the change in momentum. Impulse is denoted by J and is measured as a product of force and time. As the impulse of a body is numerically equal to change in its momentum, the unit of impulse can also be expressed by the unit of momentum. Thus, the SI and CGS unit of impulse are Newton second and dyne second respectively. In karate, a man can break a brick with his bare hands, even though the mass of his hand is small. The high acceleration of the strike provides enough force of high magnitude to his hand to break the bricks. This large force acts on the brick for a short duration, making an impulse. This impulse helps to break the bricks. This brings us to the end of this lesson on momentum and the second law of motion. Hope this session provided you with an understanding of the concept of momentum and Newton's second law of motion. Now you can use the mathematical expression for force to solve problems in physics. The section on solved problems provides you an opportunity to review some model problems based on these concepts. To revisit the key points covered in this lesson, please review the flashcard at the end of this lesson.